Swayam Prabha. Digital India. Educated India.
Good morning, good afternoon, and welcome back. We are in our series of lectures on analysis and design of rigid pavements. Now, we are currently in module 4 of the lectures. So, module 1 was an introduction. In module 1, we learned that there were 4 types of rigid pavements broadly: jointed plain concrete pavements, JPCP, jointed reinforced concrete pavements, JRCP, continuously reinforced concrete pavements, CRCP, and pre-stressed concrete pavements, PCP. Now, we learned that JPCP is by far the most common type of concrete pavement or rigid pavement, and CRCP, while not as common, can also be found in several applications. So, most of our class was devoted to JPCP, a little bit on CRCP. We haven't actually gotten there yet, we will very soon. But the truth is that CRCP analysis and design very closely tracks that of JPCP. So, while I haven't discussed too much of JPCP, too much of CRCP, we have actually done quite a lot of it because it goes along with JPCP. Now, JRCP and PCP are specialized, and in case of JRCP, extremely rare applications. So, we're not actually going to learn it in this class. So, that's what we learned in module 1. In modules 2 and 3, we learned how to analyze rigid pavements. So, the analysis of rigid pavements, as we learned in the previous lecture, basically means how do we calculate its performance. And performance, not always, but in a way, means how do we calculate the stresses. In module 2, we learned how to calculate stresses under loading for using classical methods. So, a classical method is basically an old method. Those are methods which were developed starting with Westergaard's theory almost 100 years ago. And in those methods, the final answer, what we get is a nice and clean formula, which we call an analytical solution. The analytical solution is one which we can solve by hand if you want to. We can also solve it using a calculator. We could solve it using a spreadsheet, but we do not need to have any sophisticated computer programming. So over there, we saw Westergaard's theory. We saw several updates to Westergaard's theory. Those were for the analysis of an individual slab. And then we also saw Freiberg's theory. That was the analysis of joints with dowels in particular. Not just one dowel, but a series of dowels and how they fail. We also saw how we can take into account stresses due to climatic effects. Now, when we moved to module 3, we were still on the analysis of rigid pavements, but in this case, we learned analysis of rigid pavements using the finite element method. We learned that in many of the shortcomings of the classical methods, for example, the fact that classical methods can only account for short slabs or for long slabs, that is, slabs where the joints are very far away from the load. They include tension springs, which is a non-physical behavior, and they include circular or at best a square tire footprint, whereas actual tire footprints can be fairly more complicated than those. So we saw that for all these cases, classical methods fail. They can be overcome using numerical methods, particularly the finite element method. Now, when we learned the finite element method, we saw that first of all, we have to make a series of assumptions on the way. We know that we are starting with assumptions and we are going to get an incorrect or an erroneous solution, but we would like the solution to be small. We are okay with a small solution because as engineers, in any case, we're going to have a fair amount of variability on the field due to construction and site conditions. And therefore, it's okay if our analysis also holds some amount of error in it. But the benefit of using the finite element method was that we could overcome a large number of limitations that we would otherwise face using classical methods. So we saw that for learning the finite element method, for actually understanding everything about it, it's quite mathematically intense. Unlike classical methods where we had a nice analytical formula, numerical methods such as the finite element method require quite a bit more mathematics, and what they ultimately lead to is that when we have a partial differential equation, in our case the Sophie-Germain equation, when we have a partial differential equation, it essentially becomes a series of algebraic equations. And when I say series, I don't mean 2 or 3 algebraic equations. it can turn into hundreds of thousands of algebraic equations. Obviously, we won't solve it by hand. Now, the good part about the finite element method is, although it is fairly mathematically intense, and truth be told, in this class, you're not going to learn the finite element method. You have to take a formal class on it, especially if you're civil engineering students. I strongly encourage that. But the purpose of this class was to give you an understanding. And then what we saw at the end of module 3 was a demonstration of a computer program, IceLab, which actually implements all of the things we learned. And we saw how we can generate some very interesting plots and some fairly good solutions using the finite element method. Now, that was all about analysis. In the previous lecture, we had started module 4, which was the design of rigid pavements, in particular the mechanistic empirical design of rigid pavements. And I had explained to you what is mechanistic empirical design and what are its principles. In today's lecture, we are going to be continuing on that. We will eventually in module 4 is half the class, so we will eventually very soon in module 4 get to actual procedures for design of rigid pavements. But there are still a couple of preliminaries that we have to learn before we fully go into mechanistic empirical design. So one of those preliminaries is called fatigue theory. It's something that for those of you who are civil engineers and may have taken classes in structural engineering, you may not be fully familiar with this. Those of you in material science, possibly mechanical engineering, might have heard of this. So we are going to do a quick review of fatigue theory, in particular how it applies to rigid pavements. So in today's lecture, I'm going to explain to you what is the need for fatigue theory. And then I'll explain what is fatigue testing and introduce a very, very important term which is called fatigue damage. This sometimes we'll write as FD. So I'll explain what it is and how it is related to fatigue theory. And I will also enumerate several different fatigue models or fatigue damage models for concrete, since the course is on concrete pavements after all. So that's what we'll look at in today's lecture. Let's start with the discussion, picking up on something we left on in the previous lecture. So we know that in structural engineering, our philosophy of design, the way we actually do a design in structural engineering, is based on limit state theory. Now, limit state theory is a little bit old-fashioned term. The modern terminology for it is actually load and resistance factor design, or LRFD. What is LRFD, or load and resistance factor design? Well, suppose we are trying to design a beam. Now keep in mind, we had this discussion last time, we are designing the beam. So when we are doing a design, we don't actually have any loads. When we do design, we don't have a thickness, we don't actually have a beam. We don't have a thickness, we don't have any materials, we don't even know what the loads are. A design method has to tell us all this so that we can come up with an acceptable design, whatever it means to be an acceptable design. So suppose we want to design a beam. The first thing we have to choose, of course, is what is the material of the beam. So, of course, we will choose it's Portland cement concrete. So, that's easy to take care of. Now, what we first need from the design method is what loads should we apply. The LRFD method gives us a series of different types of loads to be considered. For example, you may have heard of these terms: dead load, DL, live load, LL, earthquake load, EL, and sometimes I at least write EQL, and some authors also write it like this. So the total load applied might be dead load plus live load plus earthquake load. There is also snow load and other types of load, so we won't go into those details. But if you remember your structural design classes, you remember that we don't just take the sum of the loads, we actually multiply them with some sort of a factor. So for example, we might put 1.0 times dead load is just an example. 1.0 times dead load into 1.2 times live load into 0.9 times earthquake load, etc. Generally, these are greater ones. So this might be 1.1 times the earthquake load. These numbers, sometimes we know them as factors of safety. And the factor of safety in case of the load is generally more than one. That is, whatever we think the load is going to be based on our design guidelines, whatever we think the load is going to be, we increase it, for example, maybe by 20%, 30% or more, so that we can take into account any uncertainty that would occur in service. So the reason it's called load and resistance factor design is that we have these loads and the loads are multiplied by a factor, which is the load factor. So DL, EL, EQL, etc., all these loads, they are multiplied by a load factor. And if you recall from those classes that you learned, there are various combinations of load factors. Sometimes you only take into account dead load. Sometimes you take into account dead load plus live load. There are several combinations that are taken into account. All of these you learn, and these are specified in various design guidelines. Now, the idea of LRFD design, the reason why the name is actually load and resistance factor is the load applied on the structural element, beam, column, what have you, the load applied on the structural element has to be resisted by the structural element. A different way of putting it is that the stresses which appear or develop in the structural element as a result of the factored loads must be less than some type of strength. And there's no unique strength. There are actually different types of failure modes, and therefore there are different types of strengths for different components. So the strength, what we say is the strength in whatever mode. So for example, if it's a beam, then we're talking about flexural strength. If it's a column, we may be talking about compressive strength, etc. But the strength is also multiplied by some resistance factor. So the stresses caused by the factored load have to be resisted by some factored strength. So the strength multiplied by the resistance factor is what we may call the factored strength. Generally, the factor of safety for the resistance factor, the factor of safety for the strength is less than 1. So we increase our load to be more conservative, and we decrease our resistance also to be more conservative. So LRFD is a conservative form of design. And in LRFD then, a design is considered to be satisfactory if the stresses caused by the factored loads are less than or equal to the factored strength. Furthermore, if the deflections caused by the factored loads are within some acceptable limit, and that acceptable limit is specified in various design codes. That's the general idea behind LRFD design. I'm sure all of you either will or have studied it as part of your civil engineering curriculum. Now, let's go a little bit deeper and look at some of the underlying assumptions in LRFD. LRFD is based on static loading. So note, I said that we'll have various combinations. We'll have a dead load, we'll have a live load, we might have an earthquake load, etc. So we'll have various combinations. And as I said, these loads are going to be multiplied by some amount of load factor in various combinations, and that's going to give us the loads that we have to consider. And for each of the loads, we calculate stresses. If the factored loads are less, or the factored stresses caused by the factored loads are less than the factored resistance, which is some factor of safety into the strength, then we say that the design is successful or the design has passed. But note, the load is assumed to be applied only once. That is, any combination of these different loadings, we apply it once. If that combination really generates a stress which is less than the factored strength, then the design is successful. So we do not have repetitive loading. We have one loading applied once. If it passes the criteria of failure, then we say that the design is successful. Under these conditions, if in service we find that the loads are also within the limits that we've prescribed, that is, if the in-service loads are actually less than the factored loads, and if the design was done correctly, and obviously if it was constructed correctly, then the structure should not fail. The structure should never fail as long as the loads are less than the loads for which the design was performed. That is a basic assumption of LRFD design. So let's talk about how this would apply to rigid pavements. If we use LRFD in structural engineering, can we use it in pavement engineering? Well, so I want you to recall some of the previous analysis we've done, whether it was using Westergaard's theory or whether it was using ISLAB or using the finite element method. Either way, I had kept stressing the point that we have something called the stress ratio. And the stress ratio, you'll recall, was the stress developed, and this is the peak tensile stress. So this was the peak tensile stress developed by FCR, which is some flexural strength. So we had seen that this ratio, which we call the stress ratio, this ratio was actually significantly less than 1 for almost all the examples, not almost actually, but for all the examples. Furthermore, in many of the examples that we looked at, we didn't actually consider the effect of dowels. Even in ISLAB, we didn't actually have time to go through an example for dowels. But take my word for it, if we had properly analyzed a realistic JPCP section, that is, if we had analyzed several slabs connected by dowels and ties, so you have good load transfer, this is what you would call a good JPCP design. So if we had analyzed this and put even a relatively heavy load, the stress ratio would have been much less than 1. Okay, so recall what LRFD says. LRFD says if your stress developed by your factored loads is less than your factored strength, then your design is successful, and as long as the in-service conditions are in line or less than the conditions under the design, the structure will never fail. Okay, so now if you're saying that for JPCP pavements, in-service conditions are such that our stress ratio is always less than 1, and you can also take it, you can also look at it, the calculations previously, but the deflections are also usually very small. They're low enough that drivers or pedestrians will not recognize that there are any deflections. Therefore, if we apply LRFD theory to JPCP under all these conditions, JPCP should never fail. Our stresses are always below the strengths, much below the strengths. In fact, our deflections are always minimal as well. So JPCP should never fail. Well, that's wonderful. That means all our concrete pavements should be perfect. As long as they've been designed properly, they should last forever without any maintenance, without any cracks developing. Of course, you will agree with me based on your practical experience, based on your practical observation, that JPCP does actually fail. They do develop cracks over time, they do develop faults over time, and other distresses, pumping, etc., which we had talked about in module 1, other distresses do develop over time. So it's not true that JPCP doesn't fail. What is true is they don't fail with one repetition. One vehicle or one pedestrian walking over the JPCP road is not going to lead to deterioration and complete destruction of the road. It takes not one repetition, it rather takes several hundreds of thousands to even millions of load repetitions to actually start getting some cracking, faulting, or some failure or distress developing in the JPCP. So what we see is then if LRFD assumes that failure occurs due to a single application of a load, if that load, if the stress developed by that factored load exceeds the factored strength, then failure occurs. LRFD theory cannot adequately explain the performance of JPCP because in JPCP, a single application of a load is causing a very small stress. It is not sufficient to cause cracking to develop or faulting or any other distress to develop. Distress actually develops progressively over time, over several hundreds of thousands to millions of repetitions of load, and that's something that LRFD theory cannot take into account. It is for these reasons that LRFD, while so successful in structural engineering, is not and cannot be used in pavement engineering. And so if we no longer have this LRFD, and I should point LRFD, it would be nice if we could use LRFD because as civil engineers, we have a lot of experience using LRFD. But since we established that we cannot use LRFD, we need some alternate theory, something else that can explain the fact that the pavement does not deteriorate or does not develop distresses immediately with one load application, but the distresses are developed progressively due to very small stresses, much less than strength developing over repeated loads. As it turns out, we do have such a theory that can explain this type of behavior. That theory is called the theory of fatigue. So let's look at some of the basic assumptions of the theory of fatigue. Okay, basically there are two assumptions. A material, when subjected to a stress that is much less than its strength. So when we have any material, and it's written here material, you could also say structure because the stress doesn't just depend on the material, it depends on the structure and the loading mechanism, etc. So instead of material, you could call it structure also. So a material, when subjected to a stress which is much less than its strength, so that is the stress ratio is much less than 1. Nonetheless, so if it's much less than 1, you're not going to develop a crack. But nonetheless, it undergoes some small amount of damage or what we call micro cracks. So for example, if we consider a beam, a simply supported beam, which has been loaded, and we put a very small amount of loading, a crack is not going to form. You would think that, okay, we have perfect elastic behavior, that we load it and we'll get a deflection and a stress that's purely developed based on Euler-Bernoulli theory or any other elastic theory. In practice, what's actually happening, if you zoom down, and this has been proven through a variety of techniques, if you go in, what you'll see is that actually very small micro cracks. It's very difficult, it's not possible to see it through your naked eye. You might be able to see it using, say, some kind of a microscope, or there are other techniques. There's a particular technique called acoustic emissions, which is actually based on sound being generated. So there are a variety of techniques in the past which have established that although the material is still within the elastic range, some tiny amount of cracking, and that could be, for example, if we have concrete, we might have some aggregates. In between the aggregates, we have the paste, or we have the mortar, and it's possible that the cracking might happen here in a tiny segment, which is generally called the ITZ, interfacial transition zone. It could be that a small amount of micro cracking has developed over there. It's so small that it's not a macro crack. You cannot see a proper crack developing, but nonetheless, due to this small amount of load which has been subjected to, so a small amount of stress which has developed, these micro cracks do develop. That's for first assumption. And the second assumption, when subject to cycles of such small stresses. So yes, with each stress application, you just have a tiny crack which develops, a micro crack. But as you apply hundreds of thousands to millions of such repetitions, the material starts to lose some strength. So with every repetition, a micro crack is developing, and as a result, very small extent, the material is starting to lose its strength, or it is softening. And softening is a qualitative term, although we will see that it's possible to actually quantify it also if you're talking in terms of stiffness. But with every application, the material loses a little bit of strength, and that's what we call softening. So these are the two assumptions of fatigue theory. One, when a single load application, which is much less than the strength, is applied, then a small number of micro cracks start developing. And two, as these micro cracks continue to develop due to cyclical application of loads, that's a very important term I'm putting over here, cyclical application of loads. Due to the cyclical application of loads, when these small micro cracks keep developing, the material is actually little by little starting to lose its strength, that is, it's starting to soften. These are the two basic assumptions of fatigue theory. Now, one example, if some of you might have learned this in your BTech class, one example of fatigue theory is, for example, if you take an aluminum rod, you can actually try it, but please take permission from whoever owns the rod. If you actually take an aluminum rod and you try to break it at one go, it's very difficult to do it. In fact, by hand, it's basically impossible to do it. But instead of that, if you start applying it to small loads, if you just move it a little bit and bend it a little bit, you'll see that after several such applications, you are able to break the rod into two. So you are not able to break the rod by applying one strong load, because you need a very high amount of load for that to happen, but you are able to do it by applying over several cycles very small loads. That's a very common and typical example to show fatigue. That is, of course, for aluminum rods, but it is perfectly possible that to use the same theory to characterize concrete as well. So one question, now that we have seen what are the assumptions of fatigue theory, do these assumptions resemble the behavior of JPCP? Remember, when we apply a theory, there are many theories which can be applied. When we apply a theory to a material or a structure, we have to ask ourselves, are the assumptions of our theory valid to the case for which we are applying that theory? So, although I'm giving you the assumptions of fatigue theory, and I'll already tell you we use fatigue theory to analyze JPCP, you should not blindly assume that's correct. So, let's see. The first assumption says that when the material is subjected to stress, which is much less than the strength, these micro cracks develop. As I said, that using a variety of techniques, whether visual, whether audio, several techniques have shown that this indeed is what happens, that in concrete slabs or in concrete beams, application of this small amount of stress does indeed lead to a development of cracks, two, or micro cracks. And two, as we shall see, several tests have also showed for concrete beams as well as for concrete slabs that when you apply cyclical loads, the stiffness of the material decreases. That is, with each load application, if it's the same amount of load which is being applied, for each load application, the deflection of the beam, so if I take the beam and I apply this cyclically, if I apply the same amount of load over and over again, as I continue to increase the number of load applications, the deflection of the slab actually increases, which is just a different way of saying that the slab has begun to soften, and that particular behavior then matches the second assumption of fatigue theory. So at least on that level, we can see that yes, it seems that the observed behavior of concrete beams, slabs, and thus for JPCP, the observed behavior does indeed seem to match the expected the assumptions behind fatigue theory. So that tells us we should probably use fatigue theory to analyze JPCP pavements. Okay, So, couple of things about fatigue theory. So, fatigue theory inherently assumes many load repetitions, and I had used the term previously, cyclical loading or cyclical load repetition. That is, the loads are being applied in cycles. Why is this applicable to JPCP? Well, if you consider that I have a slab and the fact that I have some load applied to it, these loads are coming from vehicles. You have one load, the vehicle moves, and then another one takes its place. So if you just look at one point on the JPCP, it's loaded, unloaded, and so on as vehicles keep going. And therefore, inherently, JPCP pavements, and all pavements for that matter, inherently are subjected to cyclical loading. So that's another piece of evidence that it's a good idea to use fatigue theory, which after all is based on cyclical loading. It's a good idea to use fatigue theory for the analysis of JPCP sections. Now, when we say that we want to use the theory, then we have to come up with a series of tests that we can perform which are related to the theory. So for LRFT design, you may recall I had talked about strength. So if you're talking about a beam, then for a beam, we basically mean flexural strength. How is flexural strength measured? Well, if you recall, there are two methods basically. There's 2-point bending and there's 3-point bending. There's 3-point bending and there's 4-point bending. So if this is a simply supported beam, some standard shape and size, those are all specified in various standards. We could load it in the middle. This is what we call 3-point bending. 3-point because the two reactions or the two supports give us the 2 points and the point of loading is the third point. So we can use 3-point bending. We basically run the test, so we monotonically apply the load until a crack forms. Once a crack forms, we say the beam has failed. Whatever the maximum load was, if we divide it by the cross-sectional area, then we get what is the, divide by the cross-sectional area or calculate the flexural stress. Then we end up getting what is the strength or what is the nominal strength of this structure or this beam in this sort of loading. Another technique for flexural loading is what we call 4-point bending. So this is 4-point. That is, we don't apply a load in the middle. Instead, we kind of distribute the load a little bit, and effectively it's applied at 2 points. So this technique is called 4-point bending. You get slightly different results whether you use 3-point bending and 4-point bending. But the point is that if we use LRFT, then we have to know what the flexural strength is. If we're talking about LRFT for beams, we have to know what the flexural strength of the beam is, and so we have to conduct this 4-point bending or 3-point bending test. So what about for fatigue theory? So if you're using fatigue theory, and fatigue theory is based on the concept of cyclical loading, then obviously we have to have some different tests. This 3-point bending or 4-point bending flexural strength tests that we've all learned in our earlier classes, they do not assume any cyclical loading. They assume monotonic loading, that is, the load is continuously being applied. There is no cyclicalness, or the load is not being applied and removed and applied and removed. That's what a cyclical load would look like. So naturally, we can't use this monotonic test for fatigue theory. We therefore need some type of cyclical test. And these monotonic tests, by the way, are sometimes also called static tests. In the sense, there are no cycles of loads which are being applied. Now, as it turns out, almost all static tests can have a cyclical counterpart. That if given a static test, there is a way, almost all static tests, given a static test, there is actually a way to create a cyclical test out of it. It's fairly simple. You just have a number of more testing conditions and parameters that you can choose from. So let's see how we could convert this 3-point or 4-point flexural strength test, which is a static test, into a cyclical test, which then we might be able to use for fatigue theory of concrete slabs. So since JPCP mainly undergoes bending, we understand that we should have a cyclical bending test. So if we know that the mechanism of load transfer in JPCP is through bending or flexure. And now we've established that we're going to use fatigue theory in order to analyze JPCP. And so we need to come up with a cyclical bending test. Now, the bending test or the flexural strength test, it gives us FCR. That's when you apply a monotonic load. Naturally, when you use JPCP and then apply a cyclical load, you're not going to get a flexural strength. So we'll have to think about what are we going to get. It's not going to be the same test in the sense that, well, firstly, it's not exactly the same configuration. We have cyclical loading. But more importantly, it's not the same test because we are going to get a different number out of the test. And we'll have to see what that number is, which we'll do shortly. So static bending test, I had already pointed out, is 3 or 4-point bending test. and it gives us the flexural strength, which sometimes we can also call the maximum nominal strength under bending, that is FCR. The cyclical bending test is also similar. What it means to say similar is the geometry of the beam that we test, which is a standardized geometry, that is similar. The position of, so generally we have a beam of this sort, and then we allow a little bit of overhang in this test. That's for practical reasons. So, and then we have the simply supported kind of system over here. So this is generally with the correct dimensions. This is what a beam for standard beam for third point or four point bending looks like. And so this particular test, the cyclical version of it looks exactly the same. So the beam is of the same size. All the requirements in terms of where to place the loading, etc., are same. So whether it's third point or whether it's 4-point bending, either way, the configuration of the test is same. What changes is the type of loading which is applied. So one thing to understand is when we are applying a load in static testing, we might apply a constant amount of load, or we may apply it in displacement control and just measure the load. In fatigue theory, however, we apply a certain load so that we get a certain stress ratio. So we start with a target of having a stress ratio. Now, keep in mind, if stress ratio is sigma over FCR. So if we are actually using a stress ratio as our method of running the test, then we have to know FCR. So generally, before you conduct a fatigue test, you also have to conduct a static loading test. So we conduct a static loading test, we calculate this FCR or the flexural strength, and then we choose a particular value of stress ratio. So for example, if the stress ratio we chose is 0.1, then we are saying that the maximum tensile stress that we want to develop in the beam, in the original uncracked beam, is 0.1 into FCR. And then based on that, we can calculate what is the appropriate load P that we're going to apply. So we choose a value of SR, and generally we choose several values. We don't do it only at one value. So we choose, for example, SR 0.1, 0.45, 0.8. This might be what we might call a low amplitude test. That is, we are applying a very small amount of load or a small amount of stress. This might be what we call an intermediate amplitude test. And SR 0.8 is what we might call a high amplitude test, that we are applying a high amount of load. So we might do this sort of a sweep across different amplitude, and for each amplitude then we apply a cyclical load. Now there are many versions by which this test is run. One version which I have over here is that we apply the cyclical load for some amount of time, and then we give it a rest time. So we apply it, it reaches a maximum, and then we unload it, and then we let it rest for some time. Similarly, apply, reach a maximum, then come down, and then allow it to rest. This rest period may or may not be necessary. If for testing of viscoelastic materials, it's considered very important so that we allow stress relaxation. But for concrete materials, it may or may not be necessary. You might just have a system where you have a continuous cycle of this sort. So again, when we are conducting this cyclical flexural test, in addition to all the previous assumptions we make about the static flexural strength test, we also have to make an assumption of what is the stress ratio. So that's one of our parameters. Another parameter is what is the loading cycle. That is, what is the frequency at which we are applying these loads. And generally, it has been standardized that it generally goes from 1 to 5 hertz. That is, in 1 second, you see 1 to 5 cycles of these sort of loading. And here again, so we might get a high frequency test and a low frequency test, and generally we'll get different results in all cases. So when we choose a certain value of SR, when we choose a certain frequency, we will end up getting different results because these are different testing conditions. So clearly, and we can also therefore choose what is the loading and the unloading time. That's also a certain choice that we have. So unlike a simple static flexural strength test, where it's a relatively easy test to conduct, very well standardized, and we know exactly what number we'll get, when we look at the cyclical version, it's more complicated because we have more choice of parameters. And while there are some standard choices in terms of what parameters to choose, they are generally not a single value. There's a decent spread of what value we can choose from there. So it's a somewhat more complicated test, not to conduct. To conduct also, you need somewhat specialized equipment. You need a UTM which is capable of cyclical loading. But it is a more complicated test because we have a couple of more variables that we get to choose, or parameters of the test that we get to choose, and the results then vary depending on what the parameters of the test are. So just keep that in mind. The test can get somewhat complicated, depending on how exactly you're running the test. So here is an example from a paper from 1998. Here is an example of what the test result would look like. So what they've plotted here is deflection versus load. This is very common to plot for the load versus deflection curve. I'm sure all of you have plotted in a static test. Now what they have over here, and this can also turn into a stress strain curve. So what they show over here is they apply one cycle. After, obviously you expect some amount of nonlinear behavior. So we are seeing, initially we're seeing a linear regime, and then we're going into a nonlinear regime. And then unloading takes place. And then as unloading takes place, the deflection decreases as the load decreases, but we do have a permanent set which is formed, which is that we have acquired some amount of permanent damage in this based on the test that they have. Now, they conducted for 1,000 cycles, 10,000 cycles, 6,000 cycles. You conducted for many cycles. They haven't plotted all the results. But for example, if you look at this line over here, this is for 10,000 cycles and compare it to say 6,000 cycles. It's a little difficult to see, but if you just take this loading part of it and see what its slope is, and you take the loading part at 10,000 cycles and see what the slope is, you will see that this slope is greater than this slope. That means if I call this slope the modulus, it's not exactly the elastic modulus, it's not the same thing, but if I just call this some modulus, so if I say this is E1, or let's say this is E6000, and then this is E10,000, since the slope is less, what that clearly shows is that E10,000 is less than E6000. Or another way to say that is, our material, as we continue to apply cyclical loads, as the number of cycles increases, our material is softening. It is becoming a less stiff material or a more elastic material. So it's becoming, or actually less elastic material. So it's becoming a softer material. That's clearly something we can see in these actual results from these tests which were conducted. Okay, now keep in mind, when we conduct a static load test, when do we stop the test? So when we had a static load test DUS, and maybe you're doing a 3-point bending test, when we had a static load test, we basically increase the displacement and we measure the load until a crack just forms. Once a crack just forms, we stop the test. And I hope perhaps many of you, or at least all of you, I hope, have done the test in the lab, and your lab instructor would have shown you that once the test has stopped, they would have actually shown you the crack, and it's a very clear crack that you can see forming. That's a static test. Now, in a fatigue test or in a cyclical test, so in a static test, if our failure criteria is the formation of this crack, what we call crack initiation, then similarly, we have to choose in our fatigue test what is the point at which we declare that the material has failed. This time, failure is not in monotonic loading, but failure is in cyclical loading. There are many choices for when we can say that the material or the structure has failed. The first is identical to what we use for the static test. When a macro crack is clearly visible, when you can clearly see that a crack has formed, then you can say stop the test. Now, here again, it's a cyclical load. So it will take time for the crack to form, and it's a little bit subjective in terms of when exactly the crack forms. Another option, which is actually fairly commonly used in viscoelastic materials, less commonly used, but can be used for concrete, is when the elastic modulus falls below 50% of the original specimen. So if you're applying a known load and using an LVDT, for example, we can measure what is the displacement. So given P and delta, we can actually calculate the elastic modulus within the elastic range. We can calculate the elastic modulus for each cycle. And then if we, for example, plot the number of cycles n versus the elastic modulus, we'll see that it actually decreases. So we can say that if we started with some E naught, whenever this reached 0.5 E naught, we can say that at that point, at that number of repetitions, my material has failed. So we could choose to call failure that whenever a macro crack, note I'm differentiating this between micro crack versus macro crack. Micro cracks are those tiny cracks which form inside the material, which we cannot see directly with our naked eye. Macro cracks are these sort of cracks in the beam, which we can clearly see when we look at it. And I'm assuming most of you have done this also. So either we can wait to see a macro crack developing, or when the elastic modulus falls below 50%. So we continuously calculate the elastic modulus, and when it falls at 0.5 of the initial value, we can call that to be a failure condition. There are also other definitions. There are definitions based on deflection, there are definitions based on stresses. So we won't go into all those details, but there's a whole variety of these. So when we have this failure, then we say that the material has failed, using whatever definition of failure we've used. We say that the material has failed at a certain number of cycles. Those number of cycles we always show with this simple symbol n sub f. So capital N is number of cycles, f is failure. So this nf is the number of cycles to failure, whatever failure might mean, whatever definition of failure is being used. So what did we do in the test? What we basically do is we choose a particular value of SR, stress ratio. That's basically these curves which I showed over here. So you choose some value of stress ratio, several values of stress ratio, and then for each of them, you load the beam cyclically and count what was the number of cycles until the beam failed. We call that NF. So then what we have is for each SR, we have an NF. If we plot SR versus NF, we get what is called an SN curve, a stress versus the number of repetitions to failure curve, SN curve. The SN curve is the basic output of a cyclical test. So in a monotonic test, the basic output, for example, of a cyclical loading test on, a monotonic test of flexure, the basic output is the flexural strength. Similarly, if we conduct, for example, a tension test, then the basic output of the tension test might be the elastic modulus. The basic output of a cyclical flexural strength flexural test is the SN curve of the beam or of the slab. So you can think of this as a sort of constitutive model of the fatigue theory. So when we say fatigue theory, we basically mean what is the SN curve? What are the number of cycles to failure for a given stress ratio? That's ultimately what we need out of the fatigue theory, out of this fatigue testing, which we will then use later for JPCP analysis. So what does an SN curve look like? Here again, from that same paper, I picked up this diagram. So what we see here is on the x-axis, we have cycles to failure, NF, and note this is in logarithmic scale. That's always the case. The number of cycles to failure is always in a logarithmic scale. We also have on the y-axis maximum load as a percentage of ultimate. That's basically the stress ratio. It is the stress to strength, whatever the strength might be. And then what they did is for each stress ratio, they used 3 or 4 different specimens and they plotted the number of cycles to failure over here. Naturally, you're not going to get one unique value when you conduct the test. Even for the same stress ratio, due to difference in material variability, due to minor differences, for example, in curing, etc., you're going to get somewhat different number of cycles to failure. That's fine. That's considered normal with an experimental error. So in this example, for example, they used a stress ratio of 0.9, which is very high. They used a stress ratio of 0.8, which is still high. They used a stress ratio of 0.7 and so on. And then for each of these, they counted, they ran the test, they counted the number of cycles to failure. And so then they plotted these points over here. And then they simply fit a straight line through it, but the straight line again where NF is on logarithm. So it's S versus log NF that they plotted, and then they fitted that curve to a straight line. This curve is then what we call an SN curve. So using this curve then, if you say that you have such and such stress ratio based on your loading, that could be external loading, that is vehicular loading, it could be climate-based loading, but based on whatever loading you have, if you can calculate using whatever theory the stress ratio in your JPCP, then for that stress ratio, you can calculate NF, which is the number of cycles to failure for that stress ratio. Now, one more thing I want to point out over here, what I've highlighted in this red circle down here, they have provided some extra dots. So those were other specimens that they tested. And those specimens were tested basically at a stress ratio that was less than 0.6. And they wrote here, these are specimens that did not fail. Now, that's an interesting thing. In the static testing which we know for fatigue, the static testing which we know for flexure, the material will fail at some point. We will always be able to get a flexure strength out of it. But it is seen, and it's seen in some tests, it's not seen in other tests, it really depends on the testing method. But it is seen sometimes that if you put the load, the stress ratio low enough, that macro crack actually never develops, or the modulus never actually falls below 50%. It kind of just reaches a flat value and then nothing ever changes. So it is possible in some cases, it depends on the testing, it depends on the material. It's possible in some cases that if the stress ratio is actually below a certain value, and depending on your definition of failure, it's possible in those cases that the specimen never actually fails. So two things to note over here before we go further into that. This SN curve is I wrote this log, this should be semi-log. The SN curve is a semi-log curve where we are plotting stress or stress ratio versus the logarithm of the number of cycles to failure, NF. You also want to note importantly, the slope is always negative. So in this case, the curve is as shown over here. S is equal to 93.02 minus 3.68 log NF. So this curve is always has a negative slope. And the reason it has a negative slope is actually very intuitive. What it's saying is as SR increases, as you apply a higher load or the stress ratio increases, the number of allowable cycles to failure decreases. That is, if you have a very light load, you can have essentially an infinite number of cycles to failure, which means you won't fail. Or if you have a very high load, 0.9 or above, then your number of cycles to failure is essentially going to decrease, so you will get faster failure. That I think is fairly intuitive. Heavier load, faster failure. Lighter load, slower failure or no failure at all. Another thing which I was mentioning, when the SR falls below a certain value, this stress, the number of cycles to failure essentially becomes infinite. That's a mathematical way to put it. In practice, it means the stress specimen never fails. So that macro crack never actually develops if the load is low enough. This particular limit, which again I showed over here, so it's below some particular limit. This particular limit below which for a stress ratio, the material or the structure never fails is called the endurance limit of the material. So in this case, if we find that our stress ratio is below the endurance limit, we can simply take NF then tends to infinity. Now, I should point out endurance limit is a very commonly used idea, and in the Indian procedure for designing rigid pavements, which we'll talk about several lectures later, the concept of endurance limit is used. But let me point out that all fatigue models do not have endurance limits. As I said, there's no one unique fatigue model. Depending on the stress ratio which is being applied, depending on the testing conditions, frequency, etc., you have different types of tests which can be conducted. And so some of them will yield an endurance limit, some of them do not yield an endurance limit. So don't think endurance limit is a universal concept. Just because the design standards in some countries, including ours, uses endurance limit, it doesn't mean that all fatigue theories allow the concept of an endurance limit. So some fatigue models have an endurance limit, some don't. If you're using a fatigue model which has an endurance limit, your calculations change. If you're using one which doesn't have an endurance limit, your calculations change. And we'll look at several fatigue models a couple of slides from now. So there are a large variety of fatigue curves. And when I say fatigue models, I basically mean SN curves. So there are a large number of SN curves which are available in literature. Why is that the case? Well, because it depends on the testing procedure. So frequency, what is the stress ratio applied, what is the history of the stress which has been applied, what is the geometry of the beam, although that is somewhat standardized, but you can have some certain non-standard tests either. What are the mixed designs? Again, fatigue, this SN curve can be thought of as a material property, although it also depends on the geometry and the loading type, but to an extent, it also depends on the material. So when you have different mixed designs, you will have different SN curves. Definition of failure also changes. So if your definition of failure is based on the reduction in modulus, you'll get some SN curve. If it's based on observing a macro crack and depending on how good the eyesight of the experimenter is, you can have different SN curves. So there are a large number of these models. Furthermore, in today's lecture and basically for this class, all we're studying about is the SN curves for PCC, that's plain concrete. If you're looking at RCC, that's reinforced concrete, which you'd use in structural engineering, then there are SN curves for those. Similarly, in this class, we're only looking at SN curves for flexure because basically our JPCP sections undergo bending, but it's possible to also develop such curves for compression and tension. So really, fatigue theory is a very large and varied area, and I just talked about concrete. I didn't even talk about other materials. Many other applications go into fatigue theory. If any of you are in material science, you'll probably learn more in detail about this. But for now, it's sufficient to learn what we did. So as I said, there are a large variety of fatigue models or SN curves. In this diagram then, I've given some of these models. So this is based on this paper. This is a 2005 paper which was called, the name tells you everything, Enhanced Portland Cement Concrete Fatigue Models for Street Pave. Street Pave is a particular software. It's actually online, it's a web tool. You can look it up. It's an American tool used for design of some type of rigid pavements. So this paper just summarized a variety of different fatigue models which are reported in literature. You'll see in all of them, for example, depending on how you write it around, all of them basically consist of a log NF. Over here, it might seem there's no log NF, but I can simply take a log over here, and then this power term comes outside of the logarithm. So these are basically log NF, or there's some kind of power or logarithmic model. There are two models that I particularly want to point out. The first one is here. Log NF is equal to 2 into stress ratio to the power of minus 1.22. So this is some sort of an inverse relationship between log NF and SR. The reason I want to point this out is because AASHTO, which we will talk about very quickly, very soon in a couple of lectures. So AASHTO is the body which sets pavement design standards in the US. They use this fatigue model. The second one is this relatively larger one I want to talk about. This is used in IRC 58. That's the Indian Road Congress's design code number 58, which is the design and analysis and design of rigid pavements in India. And so that's the design code which is used in India, and they use this particular model. This is actually the PCA model. Here you will notice that if the stress ratio is less than 0.45, but less than 0.55, they provide one particular relationship. If it's between 0.45 and 0.55, they provide another relationship. This should actually be greater than 0.55. And furthermore, if the stress ratio is less than 0.45, then they say the number of repetitions to failure is unlimited. So this 0.45 in the Indian model, this is actually the endurance limit. So the AASHTO model does not actually have an endurance limit. The Indian model, or the model which is used in the Indian code, does have an endurance limit. There are other models also. This R star, for example, is actually taking the history of the stress into account. So it takes a maximum stress ratio and a minimum stress ratio and takes that history into account. So that's one way to look at it. There are other simpler models. For example, the ones I've highlighted, you'll see they look very similar. It's just that these coefficients are different. These coefficients are different because at the end of the day, it's an empirical model. We've done some experiments. We've joined the points with a line. And so different experimenters can get different results for reasons we talked about during the lecture. Okay. So SN curves provide, so basically what SN curves are, I remind you, so when we're talking about fatigue theory, basically we are interested in these SN curves. So SN curves provide the number of allowable load repetitions to failure. That is, if I have a given material and I have a given load, how many repetitions of this load can I apply until my material or my structure fails? That's what the SN curves give. So this NF can be thought, it is the maximum number of repetitions to failure. From a design perspective, it can be thought of the allowable load repetitions to failure. So let's say again, let's come back to reality and see what we're talking about. If we're talking about a JPCP pavement. So JPCP pavement has a load, which is a tire of a car. The load moves, another tire comes. That tire moves, another tire comes. So you have the cyclical loading. Let's say all these tires have the same load magnitude. And let's assume that the temperature distribution through the pavement is the same during this process. So then for each tire, since each tire has the same load magnitude, it's going to generate the same critical stress. And therefore, if you divide that by FCR, it's going to generate the same stress ratio. So for a given stress ratio, SR, we have NF, which is the number of allowable repetitions, but we also have the actual number of repetitions that is related to traffic. We have the actual number of repetitions N. And so if we take the ratio between these two, the ratio of the actual number of repetitions to the maximum allowable number of repetitions, that ratio is what we call fatigue damage. So fatigue theory then gives us a number which is called fatigue damage. It is the ratio of the actual number of repetitions of the stress to the allowable number of stress repetitions, where this actual number of repetitions basically comes from traffic, and we will talk about that in a subsequent lecture. And this NF, the number of allowable repetitions to failure, that comes from our SN curve. Now, coming back to performance of JPCP, it must fail after repeated load repetitions. That is, after I have a certain combination of, for a certain combination of climate and vehicles, I know, and a certain number of repetitions of the loads, I know that the JPCP must fail. But what does it mean to fail? When we say that JPCP has failed, what does that actually mean? If I give you a JPCP and I give you some data about it, can you tell me whether it's failed or not? For that, we basically need a failure criteria. So it's well and good that now we know how to calculate stresses. We know how to calculate the allowable number of repetitions for that stress ratio. And depending on the traffic, we can calculate the fatigue damage FD. But up to the point that we're able to calculate the fatigue damage, what does it mean that the material or the pavement has failed? There are basically two criteria for failure: mechanistic criteria and empirical criteria. Mechanistic criteria I'll talk about today. The empirical criteria we'll talk about in the next lecture when we talk about transfer functions. So the mechanistic criteria is as follows. It is one that involves only calculation of fatigue damage. Keep in mind, the fatigue damage calculation is a purely mechanistic process. It's based on some simple lab experiments. Well, it's not very simple, but it's still something that can be done. It's based on these lab experiments to calculate these SN curves, which are some kind of a material property. It's also based on traffic, which is some data we can get, and it's based on these mechanistic models which we use to calculate the stress ratio. So the mechanistic failure criteria is one which involves only the fatigue damage, and the simplest and the most commonly used of these is called Miner's hypothesis. So Miner's hypothesis says is, for each load and for each climate condition, calculate the fatigue damage and take the sum of the fatigue damage over all loads and all climate conditions over the entire service life of the pavement. That number then we call the cumulative fatigue damage, writing it short as CFD. Miner's hypothesis says that failure occurs. The mechanistic criteria for failure is CFD is equal to 1. Sometimes we also call this, the CFD is sometimes also called the fatigue life consumed. So we say that there is a certain amount of fatigue life. That fatigue life is when CFD is equal to 1. So the CFD, as the pavement is in service, the CFD is the amount of fatigue life consumed. Once CFD is equal to 1, 100% of the fatigue life is consumed. And so we say that the pavement has reached failure. The main assumption of Miner's hypothesis is that damage accumulates linearly, that we take this N over NF and then we can just add it up across different combinations. That's a linear assumption. There are also other damage criteria which use some nonlinear growth criteria. But the question we should ask ourselves is, do we really care about cumulative fatigue damage? If you look at a JPCP, if you go out today and look at a section on any concrete road around you, can you actually tell me what the cumulative fatigue damage is? Is that so? Do we, when we say a pavement has failed, do we really care about what the cumulative fatigue damage is, or do we care about what we care on the pavement, that is cracking and faulting? We care about cracking and faulting, not about cumulative fatigue damage. And so we would like to know how can we relate CFD to these two, and that is when we get to our empirical criteria for failure, which comes through transfer functions. So in the next class, we'll go through this empirical criteria, and I'll introduce you to the concept of transfer functions, which forms one of the most important aspects, actually about half of mechanistic empirical design. So we'll look at that in the next lecture. Thank you.